How's everyone doing today? We're back with another session of building the MSP430 disassembler that we've been working on for the last few days. The eventual goal of this is to turn this into a binary ninja processor module so that we can disassemble MSP430 in binary ninja. There is an existing Python-based implementation. It's mostly complete, and it handles like the real instructions, but some of the lifting is incomplete, and the emulated instructions that are unique to this architecture are not handled. So some of the disassembly doesn't quite always look like what you would expect it to, though it is correct. So if you're new, don't know what's going on, MSP430 is a microcontroller architecture created by TI, Texas Instruments. These are designed for like low power embedded systems. We are working on this because of a war game called Microcorruption. I'm gonna switch back over to here. We've been working on this microcorruption game. Yeah, that's the hope. We're almost done with the single operand instructions. Once the refactor is done, we'll we have to do the two operand instructions and then figure out the lifting. I know nothing about the binary ninja low level IL, so it's going to be interesting trying to figure this out. Is there documentation on that anywhere? That actually discusses what the instructions are for the LLIL? Or is it mostly just kind of looking at the API docs and trying to figure it out? Assume that it's just probably gonna be in here. Most examples. Cool. Yeah, that'd be great. So we're not quite there. I think probably another couple days until we're at the point where we can start doing that. Is it better to get the rest of the module built, like getting all of the I guess like wiring it up and then getting the calling convention and everything set up before you start doing the lifting? Or does it not really matter like what order you do it in? Like can you like get any kind of feedback of whether or not you're lifting correctly without having the rest of it in place? Cool. Awesome. Yeah, I'll hold on to this link and cool. So yeah, probably like another 2 sessions. I think we can probably get to the point where we can do that. I'm hoping that most of we can just crank through the disassembly stuff today and then start on the actual refactoring, which is what I wanted to get done. So the control flow is all done. Like when you wire it up, like you specify like branching instructions, right? And like you specify like the control flow analysis is not done via the LLIL lifting, right? Like that's just for the analysis passes. Or does the low level IL, or is it done on the low level IL specifically? Because like I've seen, I think we can look at the current MSP430 binary ninja, like the one that Josh built. If we look at the, I think it's here. No, it's yeah. So like this is where like it specifies like all the different branching instructions, and so like this is the part that actually is how the control flow is done, not based on the LLIL. Cool. So yeah, I assume that this part will be pretty simple, like once we have instructions coming out of it. And then we got to figure out the lifting part. Anyway, I did some looking around last week after the stream, or on Wednesday, whenever it was. And I kind of figured out exactly how all of the stuff we're missing right now works. Because I wasn't exactly sure. So MSP430 instruction encoding. Is this link? I always forget which one it is, and I think this is the right one. Yeah, this is the right one. So we ended up doing all the addressing modes. So we implemented most of this. We did the addressing modes for the normal registers, so your normal general purpose registers, and we've done the PC-based registers where we found that one edge case where the ret-I instruction, for whatever reason, uses it's a special case where it uses the 0 or PC register, and it doesn't actually define the addressing mode in here. So we just added the special case here, and that's the only instruction that seems to do that. What we haven't done yet is these ones, and this is for specifically R2 and R3. R2 is our status register, and so this is all like how you track things, like when you do a comparison, or you're doing arithmetic operations and you carry or borrow. That's all done via the SR register. But the SR register does double duty here, where it's also used as a constant generator. The MSP430 has these two registers it can use as a constant generator, where when you specify the register here as R2 or R3, and you specify the addressing mode as one of these based on the register here, it will pack basically or be interpreted as the constant here. And this is used for space saving so that you don't have to provide like an actual operand after the instruction. So I think, let me log in really quick to microcorruption, and we can look at an example. Let me just do this off screen so that I don't type my password on screen. All right, we can go back to it. So any of these should be fine to look at. Basically need to find something that has like a 0 or something in it. I think this is probably fine right here. So this is not a, yeah, I've joked about that actually before, that like you could do the acoustic analysis and figure out like what it is from that. Like the papers on that are crazy, and I'm curious to see how good it actually is. I haven't actually seen it in practice, but this is like probably like the worst case scenario because you get really high fidelity audio. If I can manage to get the windows to, I have a password manager, but I'm typing the password to the password manager. All right, is it that? What's the mat? Yeah, that's it. So this is the, oh, come on. That's it, paste, okay. I know, they're gonna get the password to the password manager and then it's all over from there. So this was our instruction. It's a move byte, so we're doing addressing mode B, not addressing mode B, but we're doing a byte rather than a word. So move B, 2400 R15. So let's decode this into the decoding we have here, and we can actually see like what's going on. So CF would be, let's do this the correct way since it's all little endian. So 0, 1, 0, 0, 0, 0, 1, 1. C would be 8, 9, A, B, C. and then 1, 2, 3, 4. Then, all right. So this is our instruction right here. We can see this 2400 is literally this 2400 here. That is the operand. And so what we're seeing here is that this 0 right here, this is packed into the move B instruction so that we don't have to have two operands. So if you look here and you see like move falls into the two operand arithmetic instructions. And this was just an easy example, but like we can see like we end up packing it in. So if we decode this, the opcode is 0100, which is move. Our source ends up being 3. Is this, how wide is this? This is 4. Yeah, so source would be the third register, so it's the constant generator. Our addressing destination is, which bits are that? This is 1 bit or 2 bits? So this is what, 4, that's 16, that's another 4, that's 20, 21, 22, 23, 24, 25? Right? So oh no, these are 1 bit. Okay. So source is 3, and then we get a 1, which means it's indexed, which we know because the destination is going to be indexed right there. The BW, it's going to be 1 here, meaning that it's 8-bit, which we already know because it's move B. Our source is our AS, and so we decode this as 0, 0, which is the constant 0. And then 111 is the destination, which is 15, so for R15. So yeah, we're indexing off of R15, 2400, which is the additional word that's after here. So that's kind of like why the constant generator is used. It's so you can pack those constant values, these commonly used values, into the instruction without having to have a second argument. So let's go ahead and add in the decoding for that. What I think we're going to do, and we're going to end up changing this again at some point. Like we're going to refactor this whole thing. We need to turn this into an I8 because we can have a -1 here. And so we need to be able to have an integer, a full integer. We'll do the decoding and we'll figure out what the constant is in our decoding step, and then we'll just put in the actual value here. So we're also going to want to change this slightly. Did we not? So like we don't have an underbar here. Oh, 2 and 3, yeah, we do have an underbar, okay. So because the two registers have slightly different values, we need to do these separately. So let's start with 2. Let's just go ahead and make sure that all this still compiles and all the tests still pass. All right, so we're still good here. Let's do 3 first, just because I don't know exactly how we're going to do the label yet, and the rest of them are easy because they're all just straight up constants. So we're going to match on the source. No zero Rust, so I won't be much help with that part. Yeah, so I mean, it's been a while. Like my day job is no longer writing code every day, so my Rust is definitely kind of rusty. Like the first couple streams were just like me just like really fumbling through just like basic stuff. But I think it's gotten a little bit better. It's definitely kind of a weird language to learn, but then like once you kind of wrap your head around like some of like the weirdness of it, it starts to not be as so bad, and then your C and your C++ get a lot better because all the stuff that Rust forces you to do, like a lot of it translates to C. It's just not enforced. Like a lot of the memory management and ownership and borrowing. Like if you write your C code with like the same rules, like you don't get the compiler to enforce it or the runtime to enforce it. But if you write your code that way, your C ends up being a lot safer and more secure. So we need to match, what is it, 0, 1, 2, and 3. And I think we just need to do some addressing mode constant. So 0 is 0. One is 1. Two is 2. And then 3 is -1. Yeah, I mean, so I started using it maybe a few years ago, like shortly after like 1.0 got released, and like I've been pretty happy. It's still like really like there's some parts that just aren't quite built out yet, and so it becomes painful. And like we built a Qt-based app, and I was really hoping we could build like the app in Rust, and do the UI either in Rust or with bindings, but like the Qt bindings for Rust just really aren't there yet, and because it's all C++ based, like building a good API that's compatible is really hard. So we ended up just doing the whole thing in C++, which is a little unfortunate, but I think it still was the right choice at the time. I don't know. Yeah, like there's GTK bindings that exist, and like they're okay, but GTK on anything but Linux like just doesn't work like amazingly well. Like UI, like the rendering performance on Mac OS is awful. I know that like Inkscape, the graphics program, like they ran into serious problems with it with their 1.0 release and are still dealing with it. Why is this failing? It must be exhaust. Oh, yeah. So we just need to have an underbar here, and we'll panic this. This should never happen. We might want to go to we can do unreachable, I guess. So, this shouldn't affect any of our tests below because we're not testing. Yeah, I've seen the website. They have a bunch of those Are We Yet ones. The web one I've been watching pretty closely, and the UI one I've been watching pretty closely. And looking at the embedded stuff, like I've been somewhat involved in that. The embedded is interesting because a lot of it is built out at this point, But as soon as you want to do anything with like radios, like the Bluetooth support, any of like the other like RF stuff, it just really like isn't ready to go. And so like it's okay if you're literally just doing like sensor fusion, or you're like sending stuff over like a UART or something. But like, you know, building any kind of like real product on it like just doesn't seem like it's quite viable yet, which is unfortunate. I hope that changes in the future, but we'll see. So we don't have any tests yet that exercise this. So I'm going to go in and we're going to write some. We got to find. Maybe we'll do push. We'll do push for our constant values here, because it does take an argument and it's pretty easy to test. Yeah, I've been watching what I forget the consultancy that popped up, that some of like I think some of like the either the current core or older core members Ferris Systems, I think. I think they're doing some work in the space. I think that like if RISC-V really does take off, there's opportunity there, especially with all these new chips coming out. Like there's so much stuff that's built on Espressif and like their stuff, and because there's not really good support yet because of the licensing that Cadence has, like doing a lot of RF stuff like outside of that is not going to be really like possible. Like the NRF stuff, like that's like the low power stuff that everyone uses for Bluetooth, but like they don't really seem to care about it, and aren't really investing anything into it. And so I think that like it'll have to wait until like the community like really pops up, and then hopefully they end up like putting money into it at some point. So all right, let's do some additional tests. Push const CG0, and these I think we're just gonna be able to copy and paste these pretty much and just change the instructions slightly, because we're just changing the constant that's being used. One of the changes I do want to make here is see if we can get away with not using a vector here and instead just using a slice. I'm not sure if it's going to let us, but it will be nice. Actually, you know what? We're just going to copy this. Let's see, the opcode is going to be a push. We don't have to care about the width, but we can. Addressing mode is gonna be some addressing mode constant 0. And then we need to go and actually build out this instruction. So what is this going to look like? 0, 0, 0, 1, 0, 0, 1, 0, 0. Is it 1 for word or is it 0 for word? Okay. 0, then AS will be 0, 0, and then these two bits are the ones that end up changing right here. And then our destination, we need to use 3. So this is our instruction. So 1, 2, 0, 3. Let's run this test. All right. copy these and we'll change it for the other constants as well. That's 0. That's 1. That becomes that, which means it's 1, 3. This becomes a 1. All right. And that becomes a 2 now. All right. And we got a -1. Cool. All right. So we have everything done for the constant generator register. We got to do one more for the SR, which some of it is constants and some of it is label, which I think this means an absolute address. It's in the memory at address X. All right. So we're going to do 1. We're just going to do none for right now because I'm not exactly sure what we need to look for. I think it means we read the next argument, but I'm not 100% sure. This will be sum, addressing mode constant, 4, and then, what was it, 3? Sum, eight. And then start unreachable. Oh, come on. All right. Let's get some tests in for these. Push const SR1. We need to change, what was it? It is the source of the register at the end. So this ends up being that. So still pretty simple. So it's 1, 2, 1, 12, 12. Constant is 4. So we got none. Why did we get none? because it should be 2. Addressing mode is right before here, so yeah, it would be 2. What is that? That's 2. All right, it's good. SR. Maybe you should change the naming a little bit so that it's the actual values. 0, 1. I think that will be a little bit more clear. So 1, 2, so SR 2, 3. This is 3. Oops. So what is this? This is now 3, 2, 2, 1, 2. And this would be 8. All right. So the one thing that we don't have yet is this. We don't have this implemented yet, the label. And so to do this one, it would be that. 1, 2, 1, 2. I'm gonna set this to none just so we can verify that the test passes. Redefined. What? Oh. $22.12. I named those right? Yeah. All right, so let's figure out like what this should actually do. The operand is in memory at address X. And so are we passing in I want to find an example of this. I wonder if we can. It ends up being 12. It has to be 1212. Yeah, so can we find an example of this in here anywhere? Like this should pretty much like stand out. Maybe we look for like a ampersand. Is this it right here? This might be the same addressing mode. but maybe it's a different operand, and it's a different instruction. So it's different instruction and different yeah. You don't see the register here because it's constant. So let's see here. 4582 015C. So 0 0 1 0 0 1 0 0 0 1 0 1. Let's decode this and see what we get. This is going to be a move instruction. So 0 1 0 0 is move. AD is 0, which means that the destination is registered direct. VW is 1, and so that means it's 16 bits wide. AS is 0. As registered direct. Oh, is it 2 bits? 1 bit? With 0 1. It's indexed. No, this is. So if you look at, I was looking at source. Sources are these 4 bits. So AD is 1, which is indexed. BW is 0, so it's 16-bit. And then these two 0 0 registered direct, I guess. That's weird. Like we know that the destination is 2. What was the instruction we were looking at? It was move. It was here. Right? That's what we just looked at? Yeah. So there is a second operand there, and it's moving it to there. It's interesting. So 2 would mean that it's SR. The addressing mode is 2 bits. But the addressing mode here would be 0, and there's no 0 addressing mode for register 2. Did I do the binary wrong? It's 8. Oh, I did do it wrong. Did I? That's 4. It's 5, 8. No, that's right. And our decoding is correct. That's a to move instruction. Our source is 5, R5. Then our destination addressing is 1. I think. So 80 is 1, which is kind of weird. But BW is 0, so it's 16 bits, and then 2 bytes for AS. I guess that would make sense, because the source is 5, so it would be a register direct. So this clearly is not the right kind of instruction to be looking at for this. I wonder if we should just read this and... So the operand is in memory at address. Oh, yeah. So I guess it's like dereferencing it. The operand is in memory at address there. So I think we do have to read in the next byte. So that's weird that you... Well... How would you even use that here, though? I guess you specify that it's that register, and then you don't actually use the register. You just read the next byte and grab it. So that's fine. Let's see. It would end up being here. And this is we don't need to once complement it because it's only ever going to be it's only ever going to be a positive value because it's an absolute address. Why? Absolute needs to be a U16. All right. We're going to go with this as being maybe the correct interpretation of this. And we're going to pass in an absolute value of, I don't know, 44 hex. provide some why did that fail? Oh, there. All right, all tests pass. So we've now implemented all of the single operand arithmetic instructions, all the jump instructions, and we have all the addressing modes working for both of those. I'm going to commit this and save it. Oh, come on. All right, WSL, do your thing. Let's go. Finish implementation number 4. I'm going to go ahead and squash this down, merge it into master, and then we can start refactoring. On master. Reword it, and then we're just going to go ahead and do a fix up. All right. Come on. All right, let's let this figure everything else out. I didn't run the tests, but I guess we could run all of them one more time, make sure everything broke. I don't expect anything to have happened, but the whole point was here is that we have tests for all of this now. So when we start refactoring, aside from having to change all the tests to like the new internal representation that we're gonna have, we'll know when we break stuff, which hopefully we will not. I'm gonna get some water real quick before we jump into this. All right. We also need to write the test for this. I never did it, but the code is correct. We verified that, through all this. I'm actually curious. I've never used the code coverage stuff in here. I wonder. I don't have Gcov. I don't know how to install Gcov on Windows. Is that a thing we can do with cargo? We'll see if this works. I'm kind of curious what kind of code coverage we have right now, and if there's anything we're missing. I can't imagine we are, but maybe. I wonder if it'll do like highlighting or anything to like show us areas that like what is being covered or what's not being covered. Because like there's really not. There's not that much code right now. I mean, like we've got. All of our implementation right now is under 300 lines of code. It's the other 800 lines or 1,000 lines. Yeah, I mean, like, we've got 1,000 lines of tests for 300 like lines of code. Come on, finish up the build. How's everyone doing today? See, more people have joined. If you're not sure what's going on, we're building a disassembler for the MSP430 platform. This is a microcontroller architecture developed by TI. It's used by the microcorruption wargame that we're looking at over here as a reference for some of our assembly that we're looking at, because I don't have real firmware to grab and use as a reference. So let's see if this works. Let's see what the coverage does. It's 87% covered. Okay, so we're basically not hitting our panic cases, which is fine. It means that we're not writing bad code. So we're hitting that. If our source is 1, what register is 1? SP. That's interesting. You could learn Rust here, I guess. I'm definitely not like amazing at Rust, but we are doing it in Rust, and the Rust does compile and does run and does what it's supposed to do. Interesting. So we have special case registers here for 2 and 3. And 0. So here's 0, here's 2, here's 3. So we're not writing, we don't have any tests that exercise, it looks like 1 and 3. Okay. We can add that in as well. Let's just we'll add that. You know what? Let's just do it now. It's not that much work. We might as well. So we need to test the condition of register 0 with a source of 1 and a source of 3. We could do call, I guess. Like, I don't know if you'd ever actually use call this way, but yeah, I guess it would be like a call PC, which you might do that. Let's grab this. Call PC. What are our options here? Label. Call PC. So symbolic and immediate. We need to do call. That's going to end up being 0, 0, 0, 1, 0, 0, 1, 0, 1, 0. And then what is this? This is so 0, 1. It's 0, 1, and 0, and 1, 1. Okay. Yes, and then 0, 0, 0, 0. All right. So our instruction looks like 0, 9. We don't do it backwards. It's 1, 2, 9, 0. This is a call. And this is symbolic. Is in memory at address PC plus X. So I'm assuming that the it is like the next byte. So we can do like +2. Symbolic 2. Symbolic and immediate. It's interesting. Because we need to do, this becomes it's 8, 9, A, B. B0, 1, 2. That's interesting. So I got none. Interesting. Why did we... I don't remember why we have this this gate here for this. Like why we're checking if the operand width is greater than 0. It might have been for this case right here. If I get rid of this, we rerun this, what happens? Do all of our tests start failing or passing, or? Everything passed. So the question is, did we break something before, or do we not have a passing test for something? Do we have code coverage on this now? We should. Yeah, we do. Yeah, so I don't know if we needed those conditionals. We seem to have coverage over everything. I mean, it doesn't mean that it's right. I'm going to commit this, and I mean, I guess it doesn't seem like we're going to parse things wrong. We may end up being too permissive in our decoding and allow like invalid instructions, but I don't think we are, and I don't think we're going to treat anything wrong. We will need to add the check here to make sure that there, in any case where we do an additional read, that there are enough bytes left in our slice to do the read, but this seems we'll add that check right now. There's only a few places we have to do it. So that's fine. So the other thing that we might run into is, so right here, we are, so I guess we can tell that it's a single operand instruction, so we know that this code is correct. When we get to the point when we start doing the two operand arithmetics, a lot of this code is still going to be useful because we're going to end up reading and parsing some of it the same way, I think. And so we might end up turning some of these into functions and handling it there. Yeah, this seems good. So maybe we don't want to add the check-in right now because we don't know exactly how that's going to shake out. But we do want to start the refactoring. So I guess let's talk about why we're refactoring and what we're changing. The internal representation of the disassembled code is really bad right now. It's overly verbose in some areas and not very clear in others. It is not very easy to print out, which is something that we're not doing yet, but we're going to want to. And so I have a couple ideas about how we might want to do that. One of them, I don't know for sure if it's going to work, but it might. So in Rust, the way that you make a struct printable is you implement the display trait. Let's see if we can pull this up. So you implement the display trait, and the display trait means you have to implement like I think it's like one function. It's the fumped function, and basically like this tells the struct when you call like toString or whatever on it. This tells like the struct how to print it. So one of the approaches that we might take is, instead of having a enum here that's like enum of all the jump instructions, and enum of like a one operand or a two operand or a jump instruction, the thing we might end up doing is making one enum that is all of the instructions, and then building a struct for each instruction type. Each instruction type can have a source and destination if needed, but I mean it'll have the fields or members that it needs, and that allows us to kind of populate things as needed. The one concern I have is that it may make some of, well, I guess because of the way we have it written out, it may not be that bad. Like this, we'd end up keeping something like this where we build the individual instruction here, and then we wrap it in the instruction enum. So yeah, that's kind of the direction I'm going, because what that allows us to do is implement display for each instruction, and then for each instruction it just knows how to print itself. It means that we can encode the emulated instruction data or the logic for emulated instructions into the individual instructions. And if you don't know what emulated instructions are, that's something that's unique to MSP430 and maybe others, but it's something that we've talked about a little bit on stream. Basically, the MSP430, like all of these are the instructions that it actually has in Silicon, and these are additional instructions that you can write when you're writing code. So before you send it to like the assembler or the compiler can generate this, it can use these instructions. But these mnemonics, and their machine code like don't have separate machine code in memory. You can see here that like let's find like pop. So push is an actual instruction that is implemented in Silicon, but pop is not. Pop is an emulated instruction, and what pop does is whenever you have a move of the indirect stack pointer, so I'm following the stack pointer to whatever is there, and the plus here means that you increment. So that's just the addressing mode, is it's an indirect plus auto increment. So I'm going to the address at the stack pointer, and I'm grabbing that, I'm incrementing the stack pointer to, and then I'm copying that into the destination. That is a pop. And so if you want to write assembly, because like you're writing assembly or you're a compiler and you're outputting assembly, like you can still use pop des, so like pop R15, and it's gonna assemble correctly, but it's gonna actually assemble to this instruction. So we want to make it so that our disassembler can correctly specify these emulated instructions. And so that's why I kind of think this might be the approach we want to take, is building a separate struct for each instruction, and then letting the display handle like figuring out that logic. Because if you're if you're doing the disassembly, I mean, like, you're operating on the disassembly, I don't know. I mean, I don't know if you care that this is like knowing this is a pop instruction versus that move instruction. Like, it's not going to make a difference because the semantics are still there. Like, you can still look up the behavior of what's going to happen. And like on the binary ninja side, when we lift it, like, we really don't care. We prefer to have this in the display. Sorry, this in the display because it's more clear. But the internal representation, I don't think it really matters. And so that's kind of the approach I'm thinking. I'm going to go ahead and branch here. And we can start working on updating that. What's going to suck is that it's going to make all of our tests, like, the opcodes are not going to change. And that's one of the benefits to having all this done ahead of time, is that what we're going to decode is not going to change, and the conditions here shouldn't change, but the assertions we make once we do the decoding, we verify that an instruction was indeed returned and it wasn't an invalid instruction. The actual assertions here are going to have to get updated to whatever the new structure is. So let's go ahead and branch. Refactor. Give me 1 second. We'll hide that. All right. So I think we can get rid of these single operand things. The addressing mode we're going to hold on to for right now. And then this instruction we're going to end up getting rid of. This might be a good time to start breaking out some of this. We're going to create a new Rust file. There we go. We're going to call it instruction.rs. Yep. File is not included, module tree. Use instruction. Is it use? Yeah, the Rust module system is so fucking weird. We need to start building all these now. Where do we want to start? I guess we could start at the jump stuff. That might be the easiest way to do this. We can do J and Z. So realistically, we don't have to have the individual opcodes anymore. It's something we may want. So I don't know if Jordan's still watching. If we want to implement like an assembler, so that like Binary Ninja can do the assembly, is that done the same way? I mean, would we want to make these structures able to go back the other way into assembly, or is there some like additional stuff that we have to actually build for the plumbing there? I think we can just do like an I16. let's see here. So JZ. Basically, all these are going to be the same. JLO. JLO, JC. JN. JGE. GL, and then jump. And so this should represent all of our jump instructions. JLO, JC, JN, JGE, JL, and jump. So we have those, and let's see the other ones we have to implement. So we need an RRC swap byte, RRA, SXT, push call ret I. These don't exist yet. Let's it should be mod, right? File not found for module instruction. Oh, because I spelled it wrong. That would be why. Where's refactor rename? All right. Not sure why we need the partial EQ, but I know we do. Oh, because we're doing comparisons below. I'm going to change location to offset. It's a little more clear. So let's go ahead and update this. We'll start deleting code That might be the easier way to do this, and let's let things break. Instruction, instruction. Might want to do do we care about the condition? Like, where are we using this? Like, we're only really using this here, and we don't care anymore because we can match based on the type of instruction that it is. So I don't think that that matters anymore. Like, we don't need to have that. What we are going to want to do, though, is expose the offset for these, though. Maybe we'll want to make a trait for like a jump instruction. Impl. We're going to do this manually for now, but I think we'll end up using a trait later for it. Yeah, I think the next pass we'll end up making this a trait, and we'll just give all of these that. Maybe we can just do that. Oh my god, I always hit that. Let's associated type. The use of associated types improves the overall readability of code by moving inner types locally into traits as output types. Syntax for trait definition as follows. Type A, type B. Updated syntax to refer to these new types generally. Is this actually what we care about? Let's for the example, instruction uses associated types. let's do this first, get it working, and then do the refactor. Because there's so many broken things right now. I don't want. I want to get it into a working state before try to do that. All right. We're going to want new for all these as well. We need this code right here. A U16. Return an I16. I guess we can. That needs to be pub. Do we not have JNC yet? We do. Functions private. will hit this button every time. I never want that to go. Yeah, so I think we'll still end up doing the trait at some point once we get this functional, because I think that probably is the way to go, and it will make it so that for any kind of jump instruction, like, you can pass those things around. It probably will help for analysis at some point when that becomes something that we actually care about. But for right now, I think this will be fine, and like, the structures aren't going to change again. It's just that we'll make them all the same trait, and the offset function will get to go away. Method will get to go away. JZ new offset. JLO new offset. And I think we'll probably make some constants here for these numbers, just to have something that we can more easily refer to. So things are going to be totally broken right now, but instruction. Is it this? I mean, this is going to fail to build, but how many problems are there? Oh, there's going to be a lot. Expected function tuple struct tuple variant. So we don't need this anymore. We don't end up needing this anymore. We don't need this anymore. We need to do this. Yeah, we shouldn't have to. Maybe we do. JGE. We can just do that and get rid of that. And that fixes it. So now we can go back into here. We can update these tests. Instruction. This is a JNZ. And pretty much like the same thing all the way across. That goes away. Wait, does it not have a... Remember those public? They're not. We're getting there. This is JLO. C. JN. And this is jump. All right. We had 82 errors before. We can 64 errors. We're making progress. These are failing to compile because that types are gone. Because instruction doesn't have partial EQ, so we got to add that trait to it. Can these be cloned or not? I forget. Does this need to be some? Okay. Getting it down. So we're getting closer. Basically, all the other ones that we just did, we have to go and we have to fix now because we don't have types for them yet. So we're gonna have to go build types for RRC, swap B, RRA, SXT, push, call, red eye. Think what I want to do though is I want to create a directory or a module called instructions, and we'll break these all out into the different types. And we need a Rust file, mod rs, and we're going to move this into here. Will be inaccessible, that's fine. Pub mod instruction JSX. We're gonna refactor this. I think we're fine actually here. Do we still get 62 errors or is it more broken? We get 90. Unresolved import instructions. This is correct. Oh, it's be mod. All right. We need to move this out. Use JX. So we have to re-export it. Do we want to do this or not? What do we want to make this? So if we just do this, I think everything still works. Yeah. The question is, do we want to re-export or not? And I don't know the answer to that question yet. From an API perspective, I don't know if it really matters. But this seems fine. And these are basically all test cases that are broken now. what's not working, or what shouldn't be working right now, is this stuff where we actually build these yep. And we'll probably end up cleaning this up a little bit later, but basically we gotta go implement structs for all these. File not included. It should be. Source. And so we're probably going to want to have there be a address. Let's see. Yep, that's fine. Oh, pub mod single. That would fix it. Pub mod address mode. Use address. This can tell me it can returns. Oh. If we go back to here, so we don't need the opcode anymore. We do need to know the operand width, and we need to know the addressing mode. The operand width is U8. We might want to turn this into a an enum as well. Basically, we're just going to copy this for all of them. RC swap byte. Is swap byte one of the ones that can have a width or not? It does not. We gotta get some drives in here too. Debug, copy, and clone. Also probably want partial EQ. RA. SXT. All right. And then push. Call. Yep. And then we also need to have a red eye, which has nothing. All right, we're gonna go into here and we're gonna so this should allow us to implement like effectively like what we have currently implemented. Let's make sure that nothing is more broken than it was before. We need to do a re-export. Oh, it's addressing mode. This needs to be pub. Similar path. Sure, that's fine. Oh, we can't make these copy, which is fine. They can be cloned. This can be copy. All right, we're back. We're back to the number of tests we had failing. We now need to go and we have to rebuild all of this, basically. We don't need this anymore. So this is going to be RRC new, and it's going to be addressing mode and operand width. Expected. I don't think we can do that, unfortunately. We'll fix this in a second. Let's swap B new. Does SXT have an operand? With? Doesn't. You can't do that. And then if it's ret I, it's just ret I new. This function's private. We need to go back and fix all these. Because of course we didn't make the constructors public. Okay. SXT is still not public. All right. So we need to go figure this out. Basically, what we want to do is I guess this is how we verify. I mean, this is part of like. It means that like we're mixing our decoding and everything, but basically we can check to see if the addressing mode is none. Let's do assert. Well, so here's the thing: is we don't want to assert. We want to fail. I mean, we want it to be a yeah. So oops. Uh-oh. What is this yellow? Okay. So we're going to want to add checks here for all of these where we're unwrapping. And yep. So this is kind of gross, but yep. Some instruction ret I. Interesting enough, like the ret I one, we could probably get rid of the entire struct altogether and literally just make it a ret I, because like there's no data in it. What did I do here wrong? This takes one parameter, but two are supplied. What? Call should take one. No, it should be one more. Did I type this wrong? Did I forget a... No? Comma's there. I forgot a... All right. Yeah. So we could turn this into something that has no like we don't technically need to have a struct here for ret I because it has no data. The problem is that when we implement display, we're not going to implement display, I don't think. I mean, we might implement display on instruction itself, or like assembly on there or whatever. But yeah, like we're going to implement it on the individual instructions, I think. And so we would have to put like special logic into there for that. Like we might end up doing it later. I don't know yet. But it is something that is not happening yet. If we rebuild this, we should have a lot less problems now. And all of these are now issues that are in our tests and not in our decoding code. Something we do need to do is we need to implement partial EQ on all of these, which is driving it. So we can go here and do that. I do think we need partial EQ, but I'm not 100% sure. So we're going to do it for now, and then we can get rid of it later if we don't need it. The way we can test that is by removing partial EQ from the instruction enum. So we can rerun test here. That looks better. All right, so let's go ahead and start fixing this. Instruction RRC. And we are going to have to do a couple things. One is we didn't impl functions to read out the address width, or the operand width, or the addressing mode. We're going to have to do that. Again, this is another place where we might be able to build a trait that just provides this, and we'll probably do that. After we do this initial refactor, we can go back and do a whole other pass of like removing some of like duplicate code and boilerplate. What? Why? Oh. It would help if I did that. Cannot move. Oh, because it's not copy. That's unfortunate. So we can give it a reference, and that's fine because we don't have to ever modify this. It's always going to be a it'll always be a reference. It'll always be read only. Operand with this is just a U8 self operand width. This can be moved because it's copy. I'm going to copy these and go to all the ones that have both, and then I'll do the ones that only have one, and I'll copy just the one that's necessary. The other ones just have an addressing mode. Wait. So we're just adding these in. These are just accessors so that we can actually grab the data out of it. Actually, this is wrong. It should be the other function. It should be addressing width. All right. And then here. So this is now an RRC, and we can do operand width 0 and addressing mode. And that should be pretty straightforward. We don't need the opcodes anymore. This would be a RRC. Can I do a literal with that? Will it be okay? Yeah, all right. So this is RRC. So just got to go through here and fix up these. And I think this will be a good first pass. we're gonna do inst and width. Addressing mode. All right, so it's a little bit quicker. At least there's just so many tests we have to go back through and do. Like there might be a macro that I could write to do this, but it's not gonna be trivial. Seems good. Yeah, I mean, I think once we do this pass, we've talked about some other changes we're going to do. I think that one of the other things I'm planning is we'll end up rewriting these tests and build a big table of everything, just so that it is not so many functions and I don't have to like do all these code changes again, if I can avoid it. Or if I do have to do them, at least it's in like a table that's a little bit easier to work with. It is it's a lot of tests. And we haven't really done any kind of optimization passes. We haven't really done any kind of benchmarking or anything yet. I think we'll probably get a little bit further into this before we start doing any of that. Like this might end up using a ton of memory, like how we're writing this. So we might change some of the data types internally, or make some changes. But I think that the general approach is much better, and like we can do optimizations that aren't going to be as painful, like refactoring that won't be as painful as what we're doing here, where it's just like it's literally touching everything. I mean, like when I started writing it, I mean, it was all in one file. There was no real structure to anything yet, and like it's just we're finally building some of that and paying down some of that tech debt. So I think future changes like will not be as bad. But we'll see. Luckily, though, I mean, like we do have really good tests. We'll rerun this again when we're done. Once we have all the passing tests, we'll see where we are on code coverage, and understand like if there's other things we still need to be writing tests against to hit stuff like exercise code paths that we're not. But I kind of have a feeling like, I mean, we saw a few different edge cases that we weren't hitting, like failure cases, and we can write some tests for those. But I mean, I'm pretty confident like that the decoding right now is pretty correct for what we've implemented so far, unless we've broken stuff since. But like once this is all done here, we'll see if it makes sense to do the more refactoring passes before we jump into the 2 operand instructions or not. But I don't know. We'll see. It might not enable us to do the 2 operand instructions first. And then once we're done there, we can do another refactoring pass and then start on printing. Printing is going to be with this implementation. I don't see it being incredibly difficult. It's just a lot of code. We're gonna have to go right. We have to build a whole bunch of like a lot of the same code, which is just implementing display for like all these different places. But I don't see it as being particularly difficult. I think it should be pretty straightforward, and it might make sense to do some of the trait stuff first, just because it will make it so there's less work for us to do. I'm not sure if we'll write tests for the printing. Like that's the kind of stuff that I don't see it being particularly complicated or likely to break. I mean, as long as the data is correct, we should be printing it correctly. I mean, I guess it's, you know, if you don't make mistakes, it's always going to be correct. But yeah, we'll see. I think we're getting pretty close to the end. Getting pretty far in here, at least. I don't want to guess as to whether or not I've made any mistakes during the cleanup here and whether things are gonna succeed or not as we wrap up. So I'm basically just gonna go up and run the whole thing again, and we'll see what happens. But I think this is the last set of changes. Like once these are finished, I think all the tests are done, and the rest of the code is updates are finished. We just got to see if I broke anything else or screwed anything else up. Addressing mode. Red eye doesn't have an addressing mode or an operand width. We could just do assert equal. Oh, interesting. We actually don't even need this. I don't know if this works. It also won't work. There's a whole bunch of these that don't have operand width. I forgot about that. We're gonna have to go fix those as well. Shit. These are swampy. Getting much lower on the number of errors, though. SXT. Still call. Mismatch types. We forgot something here. So this is C. So let's fix these first. Push does have an operand width. We don't need to do that though. Push does have operand width. Call does not have an operand width. Yep, so we just gotta fix these. And here. One left, which is mismatched types, and we just need to, maybe we just do this. Oh no, we don't do that. It's instruction ret I. Mismatched types, expecting an option. Yeah, we still want to do this. Maybe some. Red I. Q. Inst is ret I. All right. Wow, we did it. All right. So the decoder is finished. We still don't have, so there's tons of comments that are missing. We still have to add like tons of that stuff. We can run the coverage stuff. We should have display coverage. What? African Suites? Yeah, sure. Uh-oh. We don't want that. I don't want that. How do I remove that? Shit. Like, this is the crazy part. Like, so addressing modes. Oh, because nothing is tested there. It's being accessed, though. And, like, these are getting called. Should get getting called. Unless we're not running... replace active suites. Okay, so that seems correct. Yeah, I mean, this is just like lines that aren't actually code. Up to backspace. And yeah, I mean, like, this whole thing is basically covered. The only things we haven't covered are these these failure cases where the addressing mode is invalid, or with unreachable positions, and that's fine. I don't even know if we could write tests for some of these because we can't encode the data for some of these, and that's fine. So we're still using all of these so we got to figure out what we're going to do about public API and like what's going to be exported or re-exported and what's not. I think the way that this is all laid out now is a lot better and a lot easier. I don't know, re-exporting it might be kind of a bad way to do this, and we want to clean it up. But like the actual layout of this seems a lot better. And the other thing we might want to do is we don't actually know how many bytes a instruction is taken. So one of the issues we might run into is like say we call decode and we decode some number of bytes, whether that's a 2-byte instruction or a 4-byte instruction or a 6-byte instruction. We're not going to know how many bytes were used, and so when we want to decode the next instruction, we're not going to know like where to start. We're probably going to need to surface that up, and I'm not exactly sure how we're going to do that yet. One thing we've talked about doing is, rather than making this an option, making it a result, we might want to return like the number of bytes used or something. So we have options, and we'll figure out kind of like what the plan is there. And this is just touched, like the number of changes here is going to be like massive. Refactor internal representation. I think we're just going to merge this as is. Yeah, so I think some of this stuff, well, I don't know, this might actually make sense to put in here just because it's really only used for the decoding step. Maybe for the encoding step, not sure what that's going to look like yet when we want to start getting to the point where we can assemble, if we ever actually do. I'm not sure if we're going to build an assembler for it or not. But I don't know. This seems like a good stopping point for today. I don't really have a lot of other interesting stuff to jump into without thinking a bit more about like the overall architecture that I want to use. I do want to read up a little more on traits and figure out exactly how to do what I was talking about doing with that refactoring to let's see. To turn make like a JXX trait that has like an offset in it, so that we don't have to implement this method for it. I guess we could try something really quick. JXX. The offset is what? It's a I16. that. And yeah, so why is this complaining? Not all trait items implemented missing T. Yeah. Yeah, it's interesting that so. Yeah, I think we'll leave this for next time. We're in a good enough place. I'm gonna wrap up for the day. Hope you all enjoyed it. Got to learn a little bit about Rust, about MSP430, and until next time, I think that we will pick up again maybe on. Might be time tomorrow for something. I'm not sure yet. Otherwise, probably Monday or Wednesday next week. Thanks. You have a good night too. I'll catch you all next time. Bye.